and microdata. So today I'm going to talk about two subjects. One is the topology and one is the theory of D modules. So at the first appearance, they look so different. So they have different origin. But if you study them closer, then you will see very close analogy or similarity. So I want to talk about this. So this topology. So this has origin in number theory. Or more precisely, arithmetic geometry. On the other hand, D modules. So this is this has come from partial differential equation. Or complex variables. So yeah, so this is from number theory, and this is from this analysis. So they have totally different origin, but I'm going to tell you they have close relationship with each other. And then these two theories, so they are started like 1960s. So this is initiated by Broad and Luc and his school in Paris. And this was started by Mikio Sato and Masaki Kashiwara in Kyoto. So about the same time, independently, of course. Okay, so let me start with this topology. So the origin of so this is a subject in number theory. So let me start with the introducing the Riemann zeta function. So let me write down the definition. So you can define this as a Dirichlet series. And you can also define this as a Euler product. So here P prime numbers. And you can define zeta function as an Euler product. And this equality is already non-trivial thing. So this is reflect the prime factorization. So in any case, we have such equality, and they have this function has many important properties like analytic continuation. Or functional equation. So equation between S and 1 minus S. So zeta function has meromorphic continuation on the whole complex plane. So this has pole at simple pole at S equal 1. Because there's infinitely many prime numbers. And the Riemann hypothesis is the statement on the zero of this function. So there are something called trivial zero. So they have zeros at negative even numbers. But and the other zeros have the other part, 1/2. So this is a Riemann hybrid. So we have this important function. But today, I will not discuss about this function, but I'm going to talk about analog in positive characteristic. So this data function, so this data function is the data function of this ring of integers. And if you study some abstract algebra, so this is the principal domain, and you also have a principal domain. The polynomial ring over finite over field is also a PID. So here P is prime number. So we are in positive characteristic, and the FP is field of P element. So we consider, so we replace this Z by this ring in positive characteristic. Then we can similarly define delta function. So if we like this, so we could also like Z here. So we replace Z by this polynomial algebra. Then we have a similar definition. So like Dirichlet series. So here F rank element polynomials, but so monic means the high coefficient of highest term is 1. Then so similarly we consider Dirichlet series like this. So the polynomial of degree and the times s, and we put this as a exponent. And we also have Euler product. But here, so what is corresponding to prime numbers? So corresponding to prime numbers, we have irreducible polynomials. And we also require F to be monic. Then, similarly, degree. Yes? And the degree of F times S. And we have a similar formula. But but there is a big difference. So this function is a very mysterious function. So this satisfies nice property, but we don't know because there is a big mystery around this. But this function you can compute it easily. So this is simply like this. So this is a very elementary function. But still, there is a similarity. So here you have order to S minus 1. And from this, you can see that the poles are S equal to 1 plus 1 plus log P 2 pi I times integers. So we still have similar properties. But this function is, in some sense, too easy. So we consider in point of characteristic, there are many more objects. So you can consider rings, rings of finitely generated by P. More generally, you can consider algebraic variety over P. So I don't give a precise definition of the data function, but we can define the data function of such object in a similar way. So the data function there, so data is T of S is nothing but the data function of the affine line. So this is one dimensional object in algebraic geometry in point of characteristic. So we can generalize that definition to this object. Okay. Then so we can study such object and they under they he formulated conjectures similar to that Riemann hypothesis. So he formulated the conjecture in several statements. So, but I don't like everything. So let me just like the first one. So this zeta x of S must be a rational function of P2 minus S. So he conjectured more, but let me just stop here for the moment. So this is one of the statement in Weil conjecture. So we want to prove this. So they also suggested a possible way to prove this conjecture. So let me assume that X is projective. So this means that this is X is some variety of a projective space over Fp over some dimension. So I don't define this project, what projective means exactly, but this says that our variety is compact in algebraic sense. And also we assume that X has no singularities. So under this assumption, so they observe the following. So first, for such object, one should be able to define cohomology theory. So let me write this like this. So this is some cohomology group associated to this such geometric object. Then, so there is an operator called the Frobenius acting on this space. So this is F is called the Frobenius operator. So we are in characteristic P. So if we study algebra in characteristic P, then the operation leading function to its Pth power is a ring homomorphism. So this is a very special property in characteristic P. And we are in this algebraic geometry over characteristic P. So this fact defines endomorphism of this variety. So by non-functoriality, we have this operator acting on the cohomology also. Now, so we can consider the trace of this linear operator acting on cohomology, and so we consider the Lefschetz trace formula for this operator. So to consider this Lefschetz trace formula, we need to take the alternating sum. So Q equals 0 to 2 times D, where D is the dimension of X. And one need to take alternating sum. So I have to put a sign here. Then, so we shall have Lefschetz trace formula. Then this should be equal to the number of points of X with coordinate in Fp. So this is a certain finite set. And the alternating sum of this operator should give the number of points. And moreover, if you run finite field, then for every power of P, you have a unique extension of Fp. So if you take this extension, then you can just take the power of this operator. So we shall have such a, yes?
Minus 1 to the power Q.
Yes, thank you. Yeah. Yeah. So then you observed, there should be none. So this cohomology theory was not defined at the time of Weil. But he expects to have such cohomology theory and satisfying this formula. Then one can compute the number of points using such trace. And this has the implication that this data function, in this case, so this should be, so this is the consequence of this formula. So we have such expression. So here, this capital P of T is the characteristic polynomial of this Frobenius operator acting on the Q's cohomology. Yeah, so once we get such trace formula, then we can prove this quality. And here, this Pi, PQ are the polynomial defined as the characteristic polynomial. So as I told you, one of his conjecture says that this should be a rational function of this, but that formula immediately proves this part of the conjecture. Okay, so at the time of Weil, so this was a conjecture. But this conjecture was, so this dream of Weil was realized by Grothendieck. So Grothendieck. So he constructed this expected cohomology theory. So he defined So in his notation, it's written like this. So this is eta topology. And this QL denotes the erratic completion of the field of rational numbers. So if you take completion of the field of rational numbers with usual topology, then you just get the real field of real number. But there are some for each prime number L. So L is a prime number.
I'm sorry.
Yes.
Can I ask what's inside the determinant? 1 minus. What's inside the determinant?
Yeah. This is determinant. So this is linear operator. So you take the characteristic polynomial. So usually you put one f minus t to define characteristic polynomial, but you can also define it in this way. It's okay? Yeah, it may be defined from what you study characteristic polynomial in linear algebra class. But in number theory, it's common to define characteristic polynomial in this way. Yeah, so if A1 to AM are the eigenvalues, then you just get the product like this. Okay. So N is a prime number defined from T. And for each prime number, you have a topology of rational number, and you take completion to get a field of characteristic 0. So this is in this way one of the Bayes conjecture is proved. But there is more important one is analog of Riemann hypothesis. So that says that if the real part of 0 of Q P minus S is Q to P to half of it. So this is Dorin theorem. This is put by Dorin. And this is analog of sorry, I'm saying something wrong. Yeah, sorry. Yes. So the real part is half of this Q here. Analog of Riemann hypothesis. Yes. So in the original Riemann hypothesis, so we have only 1/2, but so this means that the ring of integer is one-dimensional object. So we have only P1. So that corresponds to that we have Q equal 1. But in algebraic geometry, we can study a higher dimensional object. So we can have more zero poles. Okay, so this is the cohomology part. So any questions so far?
Yes.
Yes.
of
Yeah.
FPM.
Yeah.
Who is X FPM?
Yeah. So in the most basic case, so we just take a file space over FP. Then in this case, in FPN over this this is capital N. So this is simply the field and you just take any dimensional vector space over this field. And in general, so we locally our variety is some subset of this. So it just take the intersection with those points with coordinate in this field. More question? Okay, so this is the number theory part. Now we go to the other side. So the other side is this D module. So here we consider algebraic D module. So we are interested in partial differential equation, but we want to write it algebraically. So we consider the ring so the first n variable are just coordinate of our complex manifold, but we also have differential operators. So here di is a partial derivation is just to the first n coordinate. So this is a non-commutative ring. But so most variables are commutative. So if you take coordinate or differential operators, then they are commutative between each other. So first only. And if I is defined from J, then stick xi and dj and d. So they are also commutative. So something happens when I call J. So di times xi. So here we get something non-trivial. So this is xi equals times di plus but you get to plus 1 here. So here you see this non-commutativity. And using this ring, we can consider a differential equation by using linear algebra. So let me write this. So this is the ring D, ring of differential operators. So we take differential operators. And we want to consider so this stands for partial differential equation. So we want to study the solution here. But now we can do linear algebra over this ring. So we consider a D module. And so this is the left. So we are working with a non-commutative ring. So we have to distinguish left and right. So here we consider left D module. So this is a quotient. quotient of this D divided by the left ideal generated by this our differential operator P. Then the solution is nothing but as so solution corresponding to the homeomorphism like this. And here O is the main D module. So this is also D module. And so we regard holomorphic functions regarded as a D module. So in this way, we can capture differential equation using a linear object. And the standard example of such a D module is given by integral connection. So this is a case where our variety is individual complex vector space. But we can work more generally on complex manifold. X. Then, so integral connections are so they are locally free OX module. So this is the sheaf of holomorphic functions of finite rank. And the integral connection is that we have Morphism called connection satisfying a certain property which I don't write down today. And so they are spanned by differential of the coordinate, and they are dual to these differential operators. And using this duality, we can regard this as a D module. And moreover, so this is an analytic object, but we have some geometric object. So we can study this mixture, and this mixture is given by the Doran complex. And this Doran complex, this integrability means that we have actually a complex. So the first one is precisely this one, and this continues up to the dimension of X. So here we believe that the theory of D modules studies this kind of object. Any questions so far? So now, so we have seen eternal cohomology arising from number theory, and this module arising from the partial differential equation. So they look so different, but now I want to say something about the analogy. So there are so today I want to talk about two types of analogy. So one is there's a formal one, so 6 operation. And the second is more mysterious one. So this is the analogy between the wide ramification so this is on the other side. And irregularities. So this is the modules. Okay, so let me start with this one. So 6 operations, yes. So 6 operation is a name after Botany. So he introduced the 6 types of factors. And he said that these 6 operations are as important as 4 operations. So 4 operations everybody knows. So addition, subtraction, multiplication, and division. And he said that the 6 operation he introduced is as important as the other 4 operations. Okay, so talk about these 6 operations, we have to work with sheaf theories. So we have seen eternal cohomology, and eternal cohomology is some certain vector space. And the vector space, so this is nothing but sheaf on a point. So if you are working on a simple geometric object as like a point, then the vector space is enough for you to go. But if you want to replace a point by more general geometric object, then you need to work with sheaf. So to define eternal cohomology, we worked on algebraic variety. Over FP. But Grothendieck said that it's more, you don't work with a single variety. So it's more important to work with more than one varieties, and you consider more similitude in them. So this is a more natural framework to study geometry. And then this sheaf theory, you have some derived category. Of sheaves on X. So today I don't give any definition of a category, but this is some linear algebra object on X. And this derived category is some category which is similar to the category of complexes. In any case, if we are given any some geometric object, then automatically you can get to such good category. consisting of such linear algebra object. So you can do, by using this category, you can do linear algebra on your variety. And once you have motion between these two geometric objects, then one can define factors like this. So this means that if you have some linear algebra object on the source, then you can send them to the second varieties. And similarly, you can pull back object on the target, then you can put it back to the first variety. So this is push forward and pull back. And so I don't tell you anything about this, but there are two types of push forward and two types of pull back. And you also have tensor product and home. So there are the six operations which are brought into this. So I started with talking about eta cohomology. So this is nothing but a case where this one is just a point. And why the point? And so this is a special case of F star over QL. So this QL is regarded as object here on the source. And if y is just one point, then you can still send your object QL here to the target. And in this particular case, you get this eta cohomology. So this is a vast generalization of the construction of eta cohomology. And in the general case, so you have motion from x to y. And if you take one point here in the target, then you have the inverse image. And so this is usually denoted like x sub y. And if you have, and you start from QL, constancy on x, then you can send it to y. And this is something, so at each point, you have a cohomology like this. And if you take other point, you get other fiber and other cohomology. And this is a C from Y, which covers everything. Which so if we specialize this object on capital Y to small y, then you recover this cohomology. And then you take other point, you get other cohomology. So this is an object like that. So this is the six operation formalism. So Grothendieck constructed for eternal cohomology. The first similarity I want to emphasize is that so we have the same formalism. For images. So here X and Y are variety of final field. But you can also consider more sort of complex manifold. And here, so this case, so we have a C of differential operators. And if you have such linear algebra object, then you can construct the derivative category. And again, if once you have such motion, then you have functors like push forward functor like this. So I just like just one operation here, but there are 5 others, and they satisfy the same formalism. So this is the first. This is formal, but very extremely useful to study the geometry of the varieties. So this is the first thing. And the second one is the wide ramification. And irregularity. So this is a local phenomena at the boundary. So if you want to study Riemann surface at the boundary, you look at the functions. So in positive characteristic, another way of this is Power series field. And so to study object on function, we study its fundamental group. And this fundamental group is generated by this monoid operator. Yeah, function, this is delta. And corresponding object here is the absolute variable. So this is a huge programmed topological group. And this has a 3-step filtration, so it looks like this. And this, on the top, there is an arithmetic part, which I ignored today. And the second part is something like this. So it's something very similar to this infinite cyclic group. So this has this allows geometric intuition. So this last part is usually denoted by P, and this is something called wide inertia. And this is the most complicated and interesting part of this also development. So let me give you just one example. So we have a finite a fine line over ft, and let's say the coordinate is x here and the coordinate is t here. Then this map, this sends t to p minus t. So this is a affine line, and affine line is in capital P. It's simply connected. So it's just a complex plane. So it's simply connected. But in capital P, we have non-trivial covering like this. So this is ununified covering. And we have the covering transformation group. So G equals this automorphism over this covering group. And this is a finite cyclic group of order P, and generated by the operation sending t to t plus 1. So if we substitute t plus 1, in here, then as I said in the beginning, so this operation is this operation preserves the addition. So it doesn't change this one. So you get automorphism here, and we have a surjection here, and this is a typical example of wide ramification. So corresponding to this, we have a differential equation. So what is the solution of this? So this is just an exponential function. So this means that you differentiate this function, but you don't. So it doesn't change from the original one. So the solution is exponential. So you can consider this D module. So of course there is no singularity in the finite, in the complex plane. But if you look at the infinity, then you have a pole of order 2. And this 2 is strictly larger than 1. So that means that you have a irregular singularity. And so I don't have time to explain more detail, but this D module and this Galois covering looks quite have some common have something common, and they look closely related. So this will come from this. So exponential function is a character of additive group. So exponential is like this, and here also have additive groups. So we have additive group, and we also have additive group. So there is some similarity between these two things. So I'm going almost out of time, so, but I want to say something on micro-local analysis. So for D module, so D module is living on your complex manifold. But this micro-local thing is you work on the cotangent boundary. So Sato and Kashiwa and others, they studied working to study D module on complex manifold. You need to work on the cotangent bundle. And there they defined something called Singer support. And prove the such inequality. And if the equality hold, then there are further objects, some objects like this, and using this you can compute the order number of the drum complex. So this started long time ago, so like a half century ago, but only recently we have a similar theory of a variety in characterized P. So still here we also have tangent bundle, and if we have object sheaf on your variety, then we can define. So this is defined by Beilinson. And also characterize cycle. So as I said in the beginning, that the theory of D module and eta homology, so they have a totally different origin, but the theory, so it took some time, but eventually we have very similar theory. Yeah, so thank you very much.
Then you can specialize on the complex side, you can specialize mod P. And there are some links between these two things.
Yeah, so this is a very interesting.
Analogy, but there is some way of connecting.
Yeah, interesting question. So, but in this picture, it's hard to. So this is just meant to be analogy. So just similarity. So there is no direct link between them. But because so here, so we have so this is related to structure sheet, and this is related to the energy sheet. So the ring looks so different. So there is no direct relation. But if you go to some periodic thing, so there is also a similarity between periodic and periodic. And once you go to periodic, then you can find more direct link between them. So in this picture, I can't see relation clearly. But if you go like this, maybe you can find more.
Are there more questions?
No, so
yes.
Maybe Bruno was asking, was thinking that for Z there are many primes and the behavior is not the same. While for complex it is it's just one behavior. So if it is irregular, it's irregular. So you're saying here that you should concentrate on things over FP. To get some some analogy.
Yeah.
Oh, yes, okay. So this S is Saito, is you, right?
Yes.
Yes. Okay. Yeah. And so this extends to like some type of Dobson-Kashiwara formula?
Yes, exactly. Thank you for asking. Yes. Yeah. So this, this is called Dobson-Kashiwara formula. Kashiwara index formula. Maybe I should have it. So index formula is a formula giving to compute this Euler number, and you can compute the Euler number using this character cycle by applying this index formula. And similarly, you can compute the Euler number of shifts in point of characteristic using character cycle. And this is given by index formula. And this index formula is a generalization to a higher dimension of the Zoltan-Shafaric formula.
Yes. And it is L-adic.
Yeah, it's L-adic, yes. Yeah.
Okay.
Thank you.
So, are there more questions? No, I called the buffet at the 7th floor in the meeting room, and now we thank the speaker again. Thank you.